So our last speaker for tonight is Mike Childress, Dr. Mike Childress, and he... You sure? He's going to talk about gravitational waves and light from a measure of neutron stars. Please welcome him up with a round of applause.
All right, can all of you guys hear me fine?
Yeah.
Relatively well? Okay, good. So, my name is Mike Childress. I'm a lecturer in the astronomy group at the University of Southampton. So I spend a lot of my time using telescopes to look at things that actually produce light in space. So I'm the least gravitationally inclined person on the panel here today. But I actually teach a couple of interesting classes, which might end up giving you some of your words on the bingo here. Photons and astrophysics, which is all about light and how light is made in the cosmos, how it propagates to us here, and then how we detect it with our telescopes on Earth. And also stellar evolution, how stars evolve, where they, how they're born, how they die, and what they leave over. And so I was particularly excited by this event I'm going to tell you about, which is the merger of two neutron stars, which is the first thing that we've ever heard in gravitational waves, and then also seen in light. All right. So I'm not going to say a lot at all about what is a neutron star, because you've heard this story a few times now. Okay? It is about 1.5 times the mass of our sun, of mostly neutrons, crammed down into a really, really tiny area, about 10 or 15 kilometers, which when I came here, everyone said this is about the size of the Isle of Wight, which I had no idea what that meant. I'm used to hearing it's about the size of Manhattan. Okay? So it's very, very compact. What I'm sort of more interested in is where do these neutron stars come from? So I'm going to tell you a little bit of the story of where they come from the stars that produce these things, and why the signal of the merger of two neutron stars was in fact such a surprise to most of the people in the community. Okay? So all of these things come from the death of a very, very massive star. So it's 1.5 to 2 times-ish the mass of our sun. But before the star produces this thing, it's extremely massive. They are always at least 8 times the mass of our sun before they produce this thing at the end of their lives. And some of them could be as massive as 20 or 25 times the mass of our sun. We still don't quite know the limit of what produces neutron stars. Okay? And some of the stuff that is produced with them is a big core, mostly of neutrons, but some of the stuff from the star likely deposits onto the top of the neutron star as well. So you may have some heavier nuclei on the surface of the star, which is actually going to be really useful for part of the conversation later on, of what we saw made when these two neutron stars collided. Okay, so I'm going to tell you the really, really short version of where do neutron stars come from, and where do they come from in the lifetimes of stars like our sun, or really stars much more massive than our sun. So all stars like our sun get energy by undergoing nuclear fusion deep in their cores. So it is hot and dense in the core of our sun. That is the perfect conditions for nuclei to slam together and form heavier nuclei. So the cores of atoms are happy to collide and get heavier and heavier, and that process actually produces energy. So our sun is in part of its life that we call the main sequence, if you have to take my class. And that is where we take hydrogen nuclei and combine them together through this really complex, ugly-looking process and produce helium. So hydrogen fuses into helium. That dumps out energy, and that energy leaks its way to the surface and comes out to us in the form of light. Okay? So it's a good thing that nuclear physics works out this way, because that's basically why we're all here. Okay, massive stars are really unique in the way they evolve, because they undergo nuclear fusion even more and more and more throughout their lifetime. So once they fuse hydrogen and helium, they do a few interesting things, reshuffle their internal structure, and then they have the right conditions in their cores to fuse helium into something heavier, which in this case is carbon and oxygen. And that process continues over and over and over again until you get this very special element of iron, which we've heard about a couple times already tonight. Okay? And indeed, in these massive stars, you actually get sort of a layered structure, this onion-like structure of all the leftovers of things that didn't actually get burnt in the previous nuclear burning process. Okay, this is the only sort of technical thing I'm ever going to show you in the talk today, because it's really central to the entire story, the beginning and the end of this merger of neutron stars. And this is how much energy you get out of fusion as a function of the mass of the nucleus that you're working with. So you start off with super light stuff like hydrogen down here, You slam those things together, and you get to move up this curve and get lots of energy by fusing elements into heavier and heavier things. When you get to the top peak of this curve, you can no longer get any more energy from slamming nuclei together. And that top of the curve is iron, which we've heard about multiple times. Okay? But we also heard today that there are things heavier in the universe than iron. You're wearing many of them now. So we have to figure out, why do we get stuff that is heavier than iron? Okay, we're going to come back to that story later on. But this is what causes the end of the lives of these massive stars, because they're used to having hot, dense zones in their cores that take nuclei, slam them together, and then take all that extra energy that comes from slamming the nuclei together. So that is how stars work. They have to get energy out of fusing things together. And once you hit iron, you can't do that anymore. So that peak there is what stops fusion in stars, and it's what ultimately leads to their death. So what is the final thing that causes the death of these stars? Well, as Niels alluded to, once you build up a significant amount of iron, once you cram the 50 million elements it was into a thimble, then you eventually have a density that is so high that the core of the star can no longer support itself against its own gravity, so it collapses. And this is what we call a core collapse supernova. So this iron core in the center of the star crushes in on itself. All those nuclei slam together, the electrons and the protons all kind of slam together. And when they do that, they produce lots and lots of neutrons, 1.5 times the mass of our sun of neutrons. They also produce lots of neutrinos, which is an interesting story in its own right. But this is the process that ends the lives of massive stars, this core collapse supernova. Okay? And so this neutron star then is the remnant of that core of iron produced in this very, very massive star. Okay, so these are really interesting things that come about at the end of a star's lifetime, and we'd love to be able to study them and understand the physics of how they work. But the way we're able to study things in the cosmos is through the light that they send to us here and that we detect with our telescopes here on Earth. At least that's the traditional way that we study things in the cosmos. So most of the time, we're used to big, bright things like our sun, which we can see even very, very, very far away. And so if we want to look at the neutron stars, which are these little itty-bitty compact remnants of the deaths of massive stars, which is even drawn too big on this diagram here, they don't have a lot of light and they're super duper tiny. So if we hope to actually see these things in the cosmos, it's not going to happen with our normal telescopes. So that's why we've got to have a new set of eyes, or really, I guess, a new set of ears, to find these things in interesting ways. All right. And what we're actually going to see with neutron stars is that really the only way we can ever detect them is when they have another friend sitting around them. In particular, the neutron stars that we see in this particular event came from 2 neutron stars slamming into each other. So I just told you the story of how we would make 1 neutron star from a very, very massive star. But the question you might want to ask is, how do you get 2 of those things next to each other? So that involves a complicated dance between 2 stars that evolve throughout their lifetimes in interesting and interacting ways. So stars will bloat out and shrink throughout their stellar lifetimes, and sometimes they get the perfect condition to send mass back and forth between their companion, and eventually one of those stars might finish burning all of its nuclear fuel. It might get that perfect condition full of iron in its core, and then explode at the end. Okay, this supernova thing will blow up here in a second. There we go. It dies in a massive explosion. What's left here is a neutron star. Okay? And this other star will eventually do the same thing, and it will hopefully have another neutron star sitting next to its little friend there. Okay? So if we want to have a merger of 2 neutron stars, we've got to be able to produce 2 of these things next to each other, which is actually really hard to do because that explosive event releases a ton of energy, and you need that energy to not blow those 2 stars apart from each other. Okay, so that's a bit of a tricky thing to do as well. In addition to that, you also have to figure out how to get the stars together to make the right conditions to actually merge in our lifetimes. So one of the really cool figures that I love from when the first black hole merger came out was people like to do a long evolutionary prediction of how do we get groups of stars together, how do they evolve with each other, how do they send material back and forth. They get these really complicated diagrams of predicting, okay, if I start with 2 stars that look this particular way and are this particular distance apart, what's going to happen to them in the end. Okay? We don't know what those starting conditions are. We don't know how they're going to interact with each other very well throughout their lifetimes. So it's really, really uncertain how many double neutron stars you should have sitting out there in the universe. And so if you want to ask how many of these things are we going to be able to hear when we turn on our gravitational wave telescopes, there's a huge factor of 1,000 uncertainty in that answer. Okay? So we thought there could be maybe 0.4 of these per year, a half of them per year, or maybe up to 400 of these things per year. We had no idea how many of these we should expect to hear. So we are very fortunate then that the spectacular event just in last August was able to happen in such a short time period. So all of us, and particularly those of us with telescopes, were very excited that this happened. All right, so why is a person with telescopes up here talking to you about what we would see from a merger of neutron stars? Well, for a long, long time, people predicted that if you have two neutron stars merging together, they should have so many energetic particles that come out of them that they should be producing very bright flashes of light. So this is a nice little simulation of the merger of two neutron stars. The final remnant here is a black hole, but you also get, along the way, a cocoon of all this very energetic material, some of which gets shot out in these super high energy jets. Okay? And those high energy jets, we think, should be ideal conditions for sending us very, very high energy light. And that high energy light is something that we call a gamma ray burst. So that is indeed the same type of event that we saw from this thing when it merged back in August of last year. So this is a movie that I think you now have seen for the third time. The two neutron stars spiraling toward each other. They've got the nice little gravitational waves. Ooh, it's very exciting, slam. And that jet of material slams out. This little cocoon here of sort of blobby stuff, I want you to keep your eye on. I'm going to tell you more about that in just a second. Okay? That jet of material is going to shoot energetic particles out, and it's going to make very, very high energy light, which we detect as gamma rays. Okay? On top of that, the actual gravitational wave signal that we got from this thing was way longer than any of the previous ones that we saw. So Emma started off telling me about the very first strong gravitational wave signal we saw. This is what it looks like for the stretching as a function of time, and all of these other ones that they found and announced shortly thereafter. This is the one we got from the neutron star. Okay? All these original ones here, the longest one was still less than 2 seconds. But this thing went on and on and on and on and on, and I'm not going to play the entire 1 minute long movie, but this movie goes on for a whole minute. Okay? So this thing was a really exciting thing for us to hear with our gravitational wave detectors. But what was really, really unique about this thing is that for the first time we were able to actually have a good idea of where we should look in the sky to try to find the light from these things. So let me tell you a little bit about how that works. Okay, so as was mentioned before, if you have two detectors, you can figure out where on the sky your signal is coming from based off of how long it takes between those two detectors getting the same signal. Okay, so the analogy I'd like to give is that maybe, so me and Emma there are probably about 3 meters apart from each other. So if we both have gravitational wave detectors sitting here, or even light detectors, and we get some signal coming to us from straight overhead, that light's going to hit us both at exactly the same time. Okay, so if the time delay between us is 0, I know the light's coming from straight overhead because I know what the speed of light is. Okay, I know it should come at the same time in this direction. All right, if the light is coming from directly along our line of sight, or 3 meters apart, that's going to take about 10 nanoseconds delay between when it hits her detector and when it hits my detector. Okay, so the maximum time difference should take 10 nanoseconds. Now, if it's something like 30 degrees above the horizon, it'll take about 5 nanoseconds between our two detectors because it'll come in at an angle, hit hers first, then hit mine. Okay, but if it comes at 30 degrees below the horizon, comes in and hits our detectors, we would have the same delay. So I can tell you how long it was between our two detectors, but I can't tell you what angle on the sky it's coming from. All I can tell you is it comes from some cone, some circle on the sky, defined by the time difference between those two detectors. So every time you combine a signal from two detectors, you get this ring on the sky that you know your signal has to come from somewhere in that ring. Okay? Now imagine you turn on a third detector. That gives you another ring from the combination of detector 3 and detector 2. Okay? And then detector 1 and detector 3 give you a third ring on the sky. And if you look for the overlap of those rings, suddenly you get this tiny, narrow little region where you expect your signal had to have come from. So that was unique because then they sent a signal to all of us all of us around the world who had telescopes and said, here's where you point your telescopes. And it was something we could actually point to instead of a giant ring. All right, and what did we see? We saw lots and lots of light. So I'll tell you about some of the light that we saw. I don't have time to tell you about all of it. But the first light that we saw was a flash of very high energy gamma rays. So this was already shown that after the chirp of the LIGO signal was detected, less than 2 seconds later we saw this bright flash of gamma rays. Okay? And this was exactly the prediction that people had had of if you slam two neutron stars together, you should shoot out energetic particles and make what we call a gamma ray burst. Now the interesting thing is that this gamma ray burst turned out to be far fainter than what people had expected you should be seeing if you were seeing light coming straight just out of that cone from the merger that I showed you. Okay? So we talked about this earlier about this was a unique, lucky event for this thing we pointed directly at us. If it only shot light out of a cone that was this small, you would expect there's like a 1% chance that it's pointing at us. Okay? But if the light is coming from sort of a bigger blobby zone here that covers a much larger region of the sky, you might have like a 1 in 3 or 1 in 4 chance of this thing pointing at us. So that actually kind of makes sense, and it's slightly consistent that we got a fainter signal from a slightly off-axis bubble of material in the kind of same direction as that jet that people predicted. Okay, so we're learning interesting things about how these gamma ray burst things happen from this particular event. Now the final part that I want to tell you about, the part that I was most directly involved in, is looking for the light at optical wavelengths. So light that we can actually see with our human eyes, and which is what we build most of our telescopes to detect around the world. So I want you to keep an eye here on this point here. This is the galaxy where this event happened. And as I'll start the movie, that will get brighter and fainter, and it will also change in color. And on the right-hand side, you'll see what we call the spectrum of the object. Okay, it's another buzzword on your bingo, which is the amount of light you get as a function of wavelength or color of the light. So it goes from blue light to red light out to infrared. And we put that through a spectrograph, which tells us basically what the spectrum of the object looks like, and that's sort of its chemical fingerprint. I'll say more about that in a second. Okay, so here's what happened. It starts off very blue, very bright, and then over time it fades away. If you look at the time scale here, it's of order a few days that it takes for this thing to fade away and get really, really red over time. Okay, so it goes from being a bluish color to sort of an orange and then red color, and it's very, very faint. All right. And this series of spectra that we took here are really, really important. This is how we found out that these things had to have gold in them. How do we know that it has gold? Well, it's really complicated, and there's about a million people who put out some sort of study about this thing. And you try to compare what's the data that we see, this black thing here, to some model that we generate in our computer of what light should come out of a giant ball full of gold and cesium and tellurium and all this weird stuff at the end of the periodic table. Okay? And sure enough, people were able to say, my computer model looks exactly like the data. So we've proved that gold was made in these explosions. Okay? And that's this is just to show you a very, very small fraction of the tons of people who wrote studies that prove that. Okay? And like we said, probably the most exciting thing that got the most press is that this made gold amongst other heavy elements. But it was really important to point out that gold is one of those super heavy things that we figure should not be produced in normal stars. So it comes back directly to this technical graph that I said is the only graph you'll see in this plot, in this whole talk, of what energy do you get out of different weight of nuclei. In stars, they don't want to undergo nuclear fusion because they're not going to get any free energy out of that. Okay? If you want to get heavier nuclei, you got to dump energy into it. So you have to have some crazy big explosion to produce that stuff. And so this is actually, I think, kind of poetic that this sort of nuclear physics that stopped the evolution of the massive stars that made these neutron stars is only overcome by the violent merger of the remnants that they had produced at the end of their lifetimes. Okay? So I thought that was really cool at this thing. Okay, and finally I'll wrap up with sort of a little, I guess, a speculation for the future of what the future holds in gravitational wave astronomy and why it's really exciting to have this new window on the universe. So if you look at the picture of the optical light produced by this particular object, and you look at it in this galaxy, it's really, really hard to see. It's a faint little dot amongst this big blobby galaxy. And normally when we point our telescopes out of the sky and try to find these kind of interesting things that pop up in the night, we see a signal of light from everything in the universe, because that's what most of our telescopes are used to checking, is the light that comes from things in the universe. And lost in this sea of light from the entire cosmos, it's really hard to see these faint little unique events. Okay, but if you listen with your gravitational wave ears, or if you put on your gravitational wave glasses as you look at the universe, instead it looks very different. You can see these things that are very distinct and lost in the crowd when you look at only the light they produce. Okay? So it was very exciting to see this from one event that we were expecting to see, and we're really excited to see what other kind of new events we weren't able to see from their light alone. That's all I have to tell you tonight. Thanks.
You know what's coming next? Has anyone got any questions?
I think I understood you to say that the gamma ray burst came 2 seconds after the jerk. If gravitational waves travel at the speed of light, gamma rays travel at the speed of light. What's that 2-second difference?
Yeah, it's a great question. So it's the time it takes for the light to get produced. Basically, the light has to interact with the matter that gets shot out of that jet. And the time it takes for that interaction to happen and for the light to sort of bounce off of all of that matter is what causes that delay. So it's got to, the light has to, that's right, the light has to get out in order for us to be able to see it. The gravitational waves just free stream through all of this stuff. So that's why you get a bit of a delay. Light leak.
If there's a cosmic microwave background to the universe, is there likely to be a gravitational wave background to the universe?
Great question. This is related to something.
Yes!
Yes. And so maybe I should throw this one over to Niels, but yes, the early universe made a gravitational wave background, which we should be able to detect. I think that's the pulsar array one.
Well,
or
so there was a claimed detection of this cosmic gravitational wave background a few years ago for something called the BICEP experiment that you might have read about, which was turned out not to be quite real. But certainly the chase is on for looking for the gravitational wave kind of counterpart. So basically little variations in density early on in the universe, we've expanded out to really big scale, and that leaves an imprint that you should be able to see in principle. And so that's what people are trying to do.
That's the point. They're more of a practical question. So the gamma ray burst came 2 seconds after the gravitational wave detection. How do you point your telescope so quick?
Good question, yes. So the lovely thing about these gamma ray burst telescopes is that the bursts are so rapid they come from anywhere on the sky that the way they design these things is wide-angle telescopes that can actually receive gamma rays from anywhere on the sky. In fact, the way that we detect gamma rays with Fermi, the instrument that does that, is the gamma ray comes in and hits a foil of tungsten, and that gamma ray hitting that tungsten actually produces a pair of positron-electron pair, which you then track the trajectory of those things after it's created. So that can come in from anywhere at any time. So yeah, it's sensitive to the entire sky.
Inside the device.
Yeah, it creates the positron-electron pair inside the device, and you track the trajectory of those charged particles that get created by the gamma ray.
We have time for one more quick question.
You said that you predicted somewhere between 0.4 and 400 events a year. How many do you see?
Well, we've got one per, what was it, a 3-year run? A three-month run. So the statistics there are pretty low, so I guess it's 1 plus or minus 1 per quarter year. Yeah.
Great. Can we have another round of applause to say thank you to Mark?